All right, we're going to get started here with the presentation on the future of flammable refrigerants. Again, I'm going to give you an overview of where we're at, where we're going, that sort of thing. I will do my best to answer any questions. What I'm going to do is give a background on how we got here, why we got here, and where we are going. An overview of where we're headed. We're going to discuss what is this refrigerant transition we're going through, what is GWP, global warming potential, and what are low GWP refrigerants. We'll discuss some of the standards that affect where we've been, where we are now, where we're going. I'll give you a little update on some of the things that are either recently completed or coming down the pipeline. We'll also go over flammability classes. One of the biggest issues that I have when we're doing these types of presentations is people having issues or concerns with the level of flammability. For most people, it's either gasoline or it's water, and that's just simply not the case. So we'll go over what it is that makes the difference between an A1, an A2, an A2L, and an A3. We'll also go into where in the industry we're going to see these flammable refrigerants and how soon. And we'll go over what you, as an industry stakeholder, need to know about these flammable refrigerants. Before we get started, I'm going to give you the two golden rules that apply to every slide and everything that I say, and they are always refer to the local jurisdiction having authority, or the AJH, when there's a code question, and always refer to the manufacturer's literature when you're installing or servicing any system. Having said that, we can proceed. Again, if there's any questions, use the question tab so I can do my best to get to them. As we mentioned, we're going through a transition. The industry is set to go through another refrigerant transition to more environmentally friendlier low GWP refrigerants. This is just a timeline of where we are, where we've been, sort of thing. Some of us should remember that the CFCs were phased out in the 90s, and the HCFCs are currently being or have been phased out, and HFCs are being set to be phased down. Now, I want to clarify the difference between phased out and phased down. Phased out means that the production and importation of that refrigerant is no longer happening, and the future supplies for that particular refrigerant will come from recovery and reclamation efforts from the industry. A phase down will reduce the production or importation of a refrigerant to a percentage of previous production or use. So shown in the graph there, on the left is the phase down, and on the right is the phase out. HFCs are set to be phased down, not phased out. So moving forward, we're going to see HFOs, HFO blends, and hydrocarbons. GWP, global warming potential, is one of the main reasons that we're seeing this transition. Global warming potential was established to provide comparisons of the global warming impacts of different gases over a period of time. CO2, or carbon dioxide, is the baseline measurement for global warming potential, and it has a value of 1. So when we look at 410A shown on the screen, it has a GWP of 2088. That means it has a GWP 2088 times greater than that of CO2. Most HFCs have very high GWP, and HFOs have lower GWPs. The lowest of all of them are the hydrocarbons, but we do sacrifice something there, as they do have a higher flammability. As you can see on the screen, HFO 1234YF is less than 1, and propane, which is 290, is around 3. Two of the main refrigerants that we've been using in our stable for the last decade or so, 404A and 410A, have very high GWPs. There you can see they are two refrigerants that are set to be affected by the phase down. This is just a chart to illustrate some of the most common refrigerants that we're currently seeing, and it'll show you the GWP, or the ozone depletion potential, that sort of thing. Currently now, the number being kicked around to be designated as low GWP is for comfort cooling right around 750 or less. And for commercial industrial applications, it's typically about 150 or less. Again, that's not set in stone. Those are just guidelines, but that's currently what's being kicked around. You should have access to this presentation in PDF format, so I don't expect you to memorize everything you're seeing on the chart here. Again, this is just for illustration purposes to kind of show you that the refrigerants we have been using have a high GWP. In this transition, we're moving to refrigerants that have a lower GWP. Due to the impact on the environment, most refrigerants are now regulated by either the EPA, state laws, or both. Equipment manufacturers have to have their products tested and approved by a testing laboratory such as UL, and refrigerant manufacturers must have their products tested by ASHRAE, EPA, or both. So a lot of these A2L refrigerants are still going to be under the purview of Section 608, still require our 608 license. Some of the hydrocarbons are going to be exempt from recovery. But what we're going to do is take a look at some of the regulations that govern refrigerant system design and use. So we're going to jump into some of the regulations and standards that have been updated that will affect the industry moving forward. Over the years, a series of international treaties, agreements, and things of that nature have been signed aimed at curbing the environmental damage caused by refrigerants. Some of us remember back to the Montreal Protocol, then we had the Kyoto Protocol, and finally the Kigali Amendment. The Kigali Amendment to the Montreal Protocol was an amendment to phase down production and consumption of HFCs worldwide. It should be noted that the Kigali Amendment has yet to be ratified by the world's three biggest HFC users, China, India, and the US. However, recently, a piece of legislation known as the AIM Act put the US in line with the Kigali Amendment. So what is the AIM Act? The AIM Act authorizes the US EPA to regulate a group of about 20 HFCs. It's a grant of authority to phase down these HFCs. It was signed by President Trump last year, and it mandated that the EPA phase down these HFCs. The goal of the AIM Act is to phase down production and importation of HFCs by about 85% over the next 15 years. And again, this is in line with what we've seen with Kigali. To point out, the reduction is estimated to impact the light commercial and residential air conditioning equipment in about 2025 and commercial refrigeration equipment from 2024 to 2026. As we move through this webinar here, I will point out and give you links to areas where you can find additional information, helpful information, that sort of thing. So again, this is a regulatory thing. It was signed and passed. It's coming down. The EPA has issued its initial ruling on the phase down, setting targets. So this is coming. It's not something that's optional. It's here and it's here to stay. SNAP 23. For those of us that don't know, SNAP is the Significant New Alternatives Policy. It's an EPA, a branch of the EPA, Section 612 under the Clean Air Act. And what they do is identify and evaluate substitutes for ozone depleting substances. Recently, SNAP 23 was approved and signed, and it contains A2L refrigerants for use in a variety of applications. The signing of SNAP 23 clears the way for replacing the high GWP HFCs in the air conditioning sector. We saw back in 2014, 2015, one of the SNAP rulings allowed R32 for use in window units, and now we're seeing it expand. There were 5 or 6 different A2L refrigerants listed in SNAP 23 as approved for use in the air conditioning sector, again, subject to use restrictions. So we've had the AIM Act signed to phase down HFCs, and we've had SNAP 23 issued, which allowed for the use of A2Ls, again, in the air conditioning side of things. So these things are streaming down the pipeline, and we got to be ready for them. A lot of the standards, the industry standards, ASHRAE, DOT, and the like have been updated to accommodate and set out the safety guidelines, so to speak, for use of these A2L refrigerants. The two main ones that we're looking at here are ASHRAE 15 and the yet to be passed ASHRAE standard 15.2. ASHRAE 15.2 is a new standard. It's the residential companion to 15. Standard 15 covers design, construction, installation, and operation of light commercial and commercial HVAC equipment and machine rooms. So 15.2 would be the residential side of ASHRAE 15. ASHRAE 15 was updated in 2019 to include the use of A2L refrigerants, and 15.2 is set to publish sometime this summer, maybe early fall, let's say September. So the standards are updated to include these A2L refrigerants. Some of the other standards that I had brought up are the UL standards. Now, the difference between ASHRAE and UL is ASHRAE standards are more for the technicians and the installers and the contractors and building to design safe systems and to be able to install and safely service these systems. The UL standards are what equipment manufacturers have to design and test to. And UL 2-40, properly known as 60335-2-40, was updated in 2019 to include A2L refrigerants, and we're also seeing 2-89, which is just like 15.2 is going to come out very soon, covers design and test specs for split-type commercial refrigeration appliances. So 2-89 is currently undergoing a revision. So we have the ASHRAE standards being updated and the UL standards being updated, again, to accommodate these A2L refrigerants that are coming down the pipeline. DOT and OSHA have issued some clarifications on what's good, what's not good sort of thing. The DOT has recently issued a clarification that up to 12 kilograms or roughly 26.5 pounds of flammable, non-toxic liquefied gas, which include our A2L refrigerants, are not subject to the requirements of a hazardous material regulation. So again, we're seeing OSHA and DOT issue some clarifications to allow for expanded use of these A2L refrigerants as long as safety conditions are met. Again, I'm going to have to say this on a lot of slides. Always refer to the local jurisdiction having authority if you have any questions about the storage or transportation of A2L or A3 refrigerants. And I will throw this out there because I know I'm speeding through this. We're trying to get through this in roughly an hour. I know your time is valuable, but if you do have questions, put them in the question section and I will do my best to get them answered in a timely fashion, either at the end of the webinar or when we're talking about it. So having looked at some of the industry standards and some of the regulatory things that are driving us in this direction, we're going to look quickly at flammability classes. And again, this is what I brought up at the beginning of the webinar about having various levels of flammability and what determines the level of flammability. What is an A1? What makes it an A2L? What makes it an A3? So this is a little bit technical. We're gonna jump in. If we get in the weeds, again, please submit some questions and I'll do my best to clarify what it is we're speaking about here. So getting into the flammability classes, there's a lot of different numbers and classifications used to identify refrigerants. It can get a little maddening. There's alphanumeric designations such as 22 or 410A or 134A, and there's also classifications based on toxicity and flammability, like A1, A2L, B3. So there's a lot of different classifications and designations assigned to these refrigerants, and it's up to the stakeholders to understand what all these things mean. When we're getting into classes of flammability, there are different levels. Some of the properties that determine flammability class are the lower flammability limit, the minimum ignition energy, the heat of combustion, and the burning velocity. And we're going to take a slide or two for each one of these to go into what these things are and how do they affect a refrigerant's flammability. So the numbers that we had thrown out there earlier, A1, B2, A3, they come from the ASHRAE standard 34 ISO 917 chart. Toxicity is used to describe the poisonous quality of a substance, and it's represented with a letter, either A or B. A is lower toxicity, B is higher toxicity. Flammability is marked with a number, 1, 2, 3, that sort of thing. Flammability indicates a substance's ability to burn, and 1 being no flame propagation. Now, I want to point this out, that just because a substance is an A1 does not mean that it is non-flammable. An A1 means no flame propagation. In a catastrophic fire, so to speak, there are a lot of things that will burn, and even A1 refrigerants will burn. So just because it's an A1 does not mean it's non-flammable. It means no flame propagation. So we've thrown here into this chart that you see on your screen a couple of the different refrigerants and where they kind of fall in the flammability chart. The 2L is a more recent designation. It used to just be 1, 2, 3, and then 2 was subdivided into 2L and 2. The higher the flammability, the higher the number the refrigerant is assigned. An A1 refrigerant would have low toxicity and no flame propagation. So far, so good. There is a question. I'll try and pull it up. That's a DOT on the 26.4. I believe that is the total per, I'm not sure if that's total per load or per system or tank. I will do some research and get back to you on that. Thank you for the question. All right, diving into these characteristics of a refrigerant that are used to discuss flammability. What helps it get, why does it get the designation A1 or A2 or A3? The lower flammability limit is one of the factors, and the LFL is the minimum concentration of a flammable substance. In this case, we're speaking of refrigerants that is capable of ignition, where we have a significant mixture of air and fuel. And it's usually expressed as a percentage. And for an example here on the screen, you're seeing I used natural gas. So in order for natural gas to combust, we have to have between 5 and 15% natural gas, and the rest has to be air. If we're outside of that window, it will not burn or explode. So if we have higher than 15% or lower than 5%, we're not going to have combustion. The same is true. Each one of these refrigerants has a range like this, a percentage range, where if we're above the upper or below the lower, we're not going to have combustion. So the LFL, again, is the range at which we can have a flame or a combustion, so to speak. Minimum ignition energy. All right, the minimum ignition energy is the minimum electrical spark energy in millijoules required to ignite a flammable gas to air mixture. Now, for a reference point, I threw the spark plug up there. The high voltage spark produces roughly between 20 and 30 millijoules of ignition energy. So I want you to keep that in mind moving forward, that when we're looking at that high voltage spark, it's between 20 and 30. So when I throw the chart up later that shows what the ignition energy is for different refrigerants, have this in the back of your head as a comparison on what it actually takes to ignite. Most 2L refrigerants are difficult to ignite because they have a higher minimum ignition energy. A lot of your household items like your toaster, the cordless drill, the hair dryer will not ignite these refrigerants. And we're also going to see that they require higher concentration levels in order to get to that flammable mixture, that little zone where we can have combustion. Heat of combustion. Again, this is once the refrigerant has been ignited, this is the amount of heat released when it burns. Class 2L refrigerants have a much lower heat of combustion than Class A3s. The heat produced by combustion of most 2L refrigerants is less likely to cause the ignition event to spread. It is possible for a 2L refrigerant to burn and not ignite other nearby flammable vapors. It doesn't produce enough heat to sustain combustion. And then finally, burning velocity. The burning velocity is the rate at which the flame front spreads relative to the unburned gas in front of it. Now, in order to be classified as a 2L, the burning velocity of the refrigerant has to be 10 centimeters per second or less, making them less likely, again, to sustain combustion after the initial ignition source has been removed. So I know I went over a lot of stuff there. We went over burning velocity, lower flammability limit, minimum ignition energy, and heat of combustion. So to kind of help illustrate these, I'm going to put some charts up and we're going to look at some comparisons. Hopefully this helps it sink in. Again, the point of this is to try and illustrate that there are differences in level of flammability. It's not just gasoline and water. There's a whole bunch in between there. So if we look at this chart, we see some of the R32, 454B, 1234YF, 717 ammonia, 152A, R290, and R600A. And what we're going to do here is we're going to compare some of the characteristics. We're going to use R32, which is an A2L, and we're going to use 290 or propane, and we're going to compare them. So if we look at this chart, again, we're looking at R32 and R290. We'll notice that the minimum or the lower flammability, the LFL for R32 is 14.4%, and for propane, it's 2.1%. That's 6 times higher. So again, we need a decent amount of R32 in the mixture at minimum in order for this thing to ignite. With propane 290, 600A isobutane, that percentage is a bit lower, even 152A. So again, it doesn't take a whole lot in the mixture to achieve ignition. The minimum ignition energy, okay, thinking back to the spark plug that we had said was 20 to 30 millijoules. When we're looking at these refrigerants, look at the minimum ignition energy. For R32, it's anywhere between 30 and 100. And the reason there's a range there is because it also depends on some of the ambient conditions and the humidity and things like that. But if we look at propane, it's 0.25. If we look at isobutane, it's 0.6 to 0.7. If we look at YF, 1234YF, which is in most of the cars being produced today, it's 5 to 10,000 millijoules. All right, so it's extremely difficult to get an ignition source that's going to ignite these. So as you can see, moving from left to right, where we have the A2Ls, and then we have an A2, and we have the A3s, that it does take quite a bit of ignition energy to ignite A2Ls. The heat of combustion. So what happens when we ignite these gases? The heat produced. All right, we can see R32 puts about 3,870 BTUs per pound, and propane is right around 19,900 BTUs per pound. So there is a very significant difference between the amount of heat generated in these flames. The heat of combustion, again, is one of the things that we look at. Will it sustain combustion? Will it cause nearby vapors or fuel sources to ignite? We can see, again, moving left to right, A2Ls, A2, A3, that the heat of combustion is on the lower side. I have one more chart here. Again, this shows along the left-hand side, we see the minimum ignition energy in millijoules, and along the bottom, we have the burning velocity in centimeters per second, and we have that 10 centimeters per second. That's the kind of target. If it's 10 centimeters or less, it'll get that 2L rating. Above that, you're either a 2 or a 3. So looking to the left, we see high ignition energy, low flame velocity. These are the A2Ls. And to the right, we see they have very low minimum ignition energy requirements, and they do burn pretty fast. Again, looking at another chart, I know I'm throwing a lot of charts. This is just, again, for comparison, so we can see how these refrigerants all stack up. This chart is divided into heat of combustion and burning velocity. Up on the left, we have the heat of combustion, and across the bottom, we have the burning velocity. You can see what the different classes. We see class 2L in the lower left, class 2 in the lower right, and class 3 in the upper right. So class 3, again, high heat of combustion, high burning velocity. Class 2, not as high as the class 3, but still higher. And then we have the 2L, and then shown up there on the left are 410A and 134A. That's just to show their heat of combustion, where they compare with other refrigerants, because they are A1s. The primary areas that we're concerned about as far as flammability are the ignition of a leak during equipment operation, the potential for refrigerant ignition during service, or a refrigerant release during a structural fire. The primary areas of concern for toxicity are a release during transit in the service vehicle or a catastrophic leak into a confined space. Now, the toxicity, that's a concern with any refrigerant, A1s, A2s, A3s. The flammability is something that we're accounting for, we're moving forward with, and making everyone aware of. So technicians, again, we should look at the SDS sheets for the refrigerant being used for guidance on recommendations for PPE, potential hazards, or hazard mitigation. For any refrigerant to ignite and continue to burn, there needs to be a competent ignition source that has enough ignition energy to light it. The correct mixture, the lower flammability, we have to be in that zone between the LFL and the UFL. We have to have a high enough burning velocity to allow the flame front to spread. We have to have enough heat from combustion to sustain the ignition and consume the fuel. So there's a lot of factors and the stars that need to align in order for the refrigerant to both ignite and continue to burn. So again, the point of this was to show that there are differences in flammability between an A1, an A2L, an A2, and an A3, or a B1, B2, B2L, B3. They are not just all gasoline or water. The conditions have to be right in order for ignition to occur and for the flame to sustain itself. These flammable refrigerants, these A2Ls, A3s that we're discussing here today, they will only be used in new systems that are designed to mitigate the risks and, again, where allowed by codes and standards. The comfort, cooling, residential, light commercial area, we will see expanded use of the A2L refrigerants such as R32 or R454B. These A2L refrigerants are already being used. We see them globally in the automotive industry. Throughout Europe, Australia, Japan, Thailand, and such, they have been using A2L systems and comfort cooling for about the last decade or so. There's roughly 100 million systems in operation. And I'd like to point out also that we're seeing R32, which is an A2L, in window units since about 2015, 2016. So it's not something that's new. The refrigerators and freezers that we residentially, buy at the store already have A3s. They have either 600A or 290 in them. These refrigerants are already in use around us. This is not something that's new. It might be new to us, but it's not new to the industry. We're just having to adjust to the transition. Again, these refrigerants, again, today are around you. They're in your car, they're in your refrigerator, they're in the local reach-in cooler at the supermarket. They're in use all over in comfort cooling systems around the world, and they're coming to comfort cooling systems here. We must account for the flammability. So one of the things that we're talking, control schemes that we're talking about, is mitigation strategies. And the mitigation strategy deployed must be able to reduce the concentration level to keep us below the LFL. This would typically include some kind of mechanical ventilation, running fans or blowers, that sort of thing. In larger systems, we're going to see room sensors, active room sensors. The older room sensors used to just sound an alarm to let you know to get out of the area. The newer active sensors will not only sound an alarm, but they will then do something. They will de-energize the unit. They will energize the unit or put the system into pump down or activate facility ventilation, something along those lines. Some of the manufacturers are looking into isolating the refrigerant charge with a solenoid or with a relief valve piped outdoors. the mitigation strategies are going to vary from one manufacturer to the next. One of the things that it should be noted is this ventilation. It's going to be one of the things that we're going to see in the standards and the codes, that depending on the charge size of the refrigerant, we're going to have some kind of ventilation, some air movement again, and this prevents the mixture from reaching the LFL and being able to be combusted. It doesn't take a whole lot of ventilation to, based on the again, AHRAE, the UL, they've been doing tons and tons of tests on these refrigerants. There's studies that have been published on the flammabilities of A2Ls and A3s, and they went out of their way to make sure that they set these things on fire and burned them completely, and they measured how much heat was produced and how much ignition energy it took to ignite them, and what kind of ventilation was necessary to prevent ignition. So we are moving in the right direction, and this is, again, based on sound science and tons of studies. I can't give them enough credit for all the studies that they've done and the money that they've put into this. On the refrigeration side, commercial refrigeration, as I mentioned earlier, we're seeing expanded use of smaller charge R290 systems, and as we know, R290 is an A3. Currently, the charge limit for systems with an A3 is right around 5.3 ounces of refrigerant. The charge limit is one of the topics being discussed in the ongoing mechanical code and standard revisions committees that are meeting as we speak. And one of the other things that affect the charge size of these, again, is the authority, the local jurisdiction having authority over it. So even with 5.3 ounces, there are some areas that local code may not want them. So again, check with the local jurisdiction having authority about the A2Ls and the A3s. But these are already out. These R290 systems, they're widespread. We can find them in most commercial applications, but they are limited, again, to packaged units, as we kind of see in the images there, and they are a smaller charge. We're going to talk a little bit about some system installation stuff, things that we can expect to see when these A2L systems roll off the assembly line and into the back of your truck and into your store or home. The installation procedures for the A2Ls and A1s are very similar. Many of the differences that do exist are pre-installation safety precautions that primarily involve evaluating the installation site. And what that means is we're looking at the cubic space, the volume of the space where we're being installed. We're evaluating if mitigation is required, those sorts of things. Again, we're also checking with the authority having jurisdiction if it's allowable. And I will also mention, defer to the manufacturer's installation guide when sizing out and installing an A2L or an A3 system. As I mentioned, these A2L systems, we have to look at the installation site, make sure that it's adequate for this refrigerant. One of the things that's going to be different from the A2L systems and the A1 is the maximum charge size. It's going to vary from unit to unit. There's not going to be a universal maximum charge size. The space where we're installing this system must be large enough and have enough air to keep the refrigerant, should it leak, at or below a percentage of the LFL. The manufacturers are required, they will be required to print charts and both charging and sizing charts in their installation literature to help with these calculations. I know nobody wants to sit and try and do the formulas that are found in some of these standards. They are some complex formulas. I spent some time staring at them and working them out, and they are pretty rough, but there will be charts designed in the installation literature to help say, okay, what's the largest space I can install this in? What's my maximum allowable charge? That sort of thing. So to help the transition, there will be a lot of information published in the manufacturer's installation, and that's a code requirement that they publish all of this information. Again, getting back to the charge, while the process of charging the system is the same, there's some additional safety factors that we have to take into consideration. We add R32 the same way we add R410A. You can charge R32 as it's a single component refrigerant as a vapor if you wish. The blends, again, we're still going to charge as the liquid. The maximum allowable charge is not a universal figure, and it will be different for every system installation. The codes and standards print charge maximum allowable charge sizes, and these are two terms that I want to familiarize you with. They are the M1 charge and the M2 charge. And again, we're allowed by code. Charging a system without ventilation installed, that's we refer to it as the M1 charge. So there'll be a weight listed, let's say 5 pounds. That is the maximum charge for this system if there is no ventilation installed. That charge can increase if the ventilation is installed, so the charge size can go from now, say 5 pounds to 10 pounds. Again, those are numbers I made up and threw out there. Each different refrigerant will have a chart, and they will have an M1 and an M2 charge. And what I'm trying to point out here is the difference between those numbers. We have to get used to seeing those numbers, M1, M2. And the difference between those two, again, is the ventilation being installed, the ventilation of the space where the system is installed, where the refrigerant components are. Again, always refer to the manufacturer's literature when we're installing these, and always check with the local authority having jurisdiction to make sure that an M2 charge is even allowed in that area. So I'm raising some points here again to get you thinking. So when these things do roll off the assembly line, we're going to understand when we read the manufacturer's installation literature what an M1 charge is and what an M2 charge is. Again, M1, there's no ventilation installed in the space. It's the space as is, and M2 is ventilation has been installed to keep the refrigerant from reaching a percentage of the LFL, airflow, air movement. So far, so good. This is a quiet bunch, by the way. So what's the same? Most of the physical and chemical properties of the A2L refrigerants are no different from the A1 refrigerants. Some of the A2L and A3 refrigerants even offer better efficiency and capacity when compared to the predecessors, the CFCs, the HCFCs, and the HFCs. So again, from a chemical property standpoint, heat transfer standpoint, we're not looking at any major differences. What's different? These low GWP refrigerants include some of the A2L. Again, let's throw this out there. Let me stop right away and say low GWP, not all low GWP refrigerants will be A2Ls. Most of them at the moment are, but that doesn't mean that all of them will be. There are other refrigerants that are low GWP that may have a different classification based on either toxicity or flammability. For example, ammonia is a low GWP refrigerant. It's classified as a B2L. So I'm just throwing A2L out there, but I want you to understand that low GWP doesn't automatically mean A2L. It means it's a refrigerant that has a low GWP. There was a question that said, will small leaks change the composition or change the LFL? The LFL for the refrigerant is what it is. In the blended refrigerants, I would have to defer to the manufacturers. When 410A initially came out, one of the main concern was fractionation and leaks, and they kind of put that to rest after doing some exhaustive studies saying that it doesn't fractionate to the point where it changes the composition and it can be topped off. So again, I will defer to the manufacturers of the refrigerants on leaks changing the composition. But if it's a straight refrigerant, say R32, it's a single component refrigerant, so there's not much to worry about. The LFL is the LFL established for the refrigerant by ASHRAE in ASHRAE Standard 34. So what do I need to know about these? Stakeholders. And when I say stakeholders, that means technicians, contractors, store owners, homeowners, anyone that's going to, even people at the supply house, storage, shipping, transportation, anyone that's going to touch these refrigerants in the food chain, so to speak, from the time they're manufactured till the time they end up in a system. That is a stakeholder. And we have to be aware and competently trained in the proper handling and mitigation of risks, again, due to the lower flammability or toxicity associated with some of these refrigerants. So an industry stakeholder could be someone that owns a grocery store, someone that works on the unit in your home, someone that sells these systems to a contractor, or the manufacturer rolling them off the assembly line. There's no end to what we can classify as a stakeholder, anyone that's going to see these refrigerants in any manner. As I brought up in the last slide, that competent training and understanding risk mitigation, training is the #1 way to ensure a successful refrigerant transition. No matter what type of refrigerant or system that a technician is servicing, installing, proper training is the foundation. All industry stakeholders involved in this ongoing transition can benefit from some kind of safety or awareness training. Having said that, ESCO, the company that I work for and am doing this webinar on behalf of, does have a low GWP refrigerant safety course. It's already up and running. There are other programs up and running as well. I don't want to state that we're the only game in town, but we are one of the games in town. We have the Low GWP Refrigerant Safety, flammable and mildly flammable refrigerant book. It's available in print and in an e-learning format, and there is a closed book 50-question safety certification exam that you can take to ensure retention. AHRAE has formed a committee with working groups to provide information to industry stakeholders and help ensure a smooth transition to these low GWP refrigerants. This information is available on the Safe Refrigerant Transition Task Force website. I'll put a link up there for you at the end of the presentation. I just want to make you aware of there's plenty of places to get information on these low GWP refrigerants, depending on how deep you're looking to get into it. If you're looking for something at an awareness level, if you're looking for in-depth information. One of the questions that came up is how exactly do they determine GWP? Again, they compare the global warming potential of a gas, the heat trapping ability of a gas over, I believe it's a 100-year period, when compared to the heat trapping ability of CO2. Now, how scientifically that is done, I couldn't say. I mean, I could probably look into it, but it is a comparison of the, again, CO2 being the baseline with a GWP of 1 and its heat trapping ability, how long it sticks around in the atmosphere over a 100-year period. And then they compare each refrigerant to CO2. How long does it hang around in the atmosphere? How long is the carbon around? And how long does it trap heat? And it is a 100-year period, yes. So in summary, we have standards and regulatory things that are moving forward onto these low GWP refrigerants. They've been updated to accommodate. We have these refrigerants being tested by UL, by the different HVAC organizations that are out there. And this information is being shared industry-wide to ensure that, again, safety is the #1 goal here, to ensure that we can safely use these refrigerants in any application and bring forward any limitations that they may have. And I'll put this slide up. This is the end of my presentation. And on this slide, you'll see a link. And again, you should have this in a download. It should be available, and these links are in there. One of them is the Low GWP e-learning course. The other is a link to the book that I wrote on Low GWP Refrigerant Safety. And that last one there is the AHRAE Safe Refrigerant Transition Task Force website. Again, on the AHRAE site, you'll see a lot of information. There's links to webinars, there's papers that have been published. And if you pay attention to any of the publications, such as the news or any of the different industry publications, there's articles, there's webinars and things that are being done, again, across the country on awareness of these particular refrigerants, what we need to know, how to prepare for them. The fact is they're coming, and we don't have to be as concerned as, again, initially. When I started doing these webinars early on, there was a lot of concern that we're going to start blowing ourselves up. Listen, the rest of the world has been using these for over a decade safely. We can do the same. I'm going to ask at this time if we have any questions. We have a small window here for some Q&A. I'm going to point out that I'm a one-man show today, so I'm trying to manage the slides and the questions and the recording all at the same time. So give me a second on that, and I will get to your questions. All right. There was someone that asked if I could comment on R1270 propylene. At this time, I can't comment on that. I don't have the information to competently speak on propylene at this time. R32 manifolds, are they any longer charging hoses? There are R32 manifolds out there now. A variety of manufacturers are making A2L equipment, recovery machines, hoses, manifolds. I don't think they're going to be any different from the equipment that we're currently using. Again, it all comes down to emissions in the particular hose. But again, when a manufacturer certifies that their equipment is A2L rated, then they've had it tested for that by either UL or a third-party testing organization. The length of the hose, I don't think it's going to play too much into it, but again, it all depends on how and where they had it tested and what the material the hose is made of. There's another question that asks, to what extent is Heatcraft in the transition to A2L and which refrigerant? That I can't comment on. I work primarily, I am on the ASHRAE Refrigerant Task Force. I'm actually the chairman of the Technician Outreach Committee, but I can ask Don to get a reply out to you via email on that particular question as far as Heatcraft. And I know they have a training program coming up as well for A2Ls. As far as the tools on A2Ls, again, the codes and standards require that whatever tools you're using be rated for A2Ls. There are a large number of these tools already on the market. Vacuum pumps, recovery machines, gauges, those sorts of things. The hand tools and things like that. Again, I don't see anything changing, but anything that has refrigerant running through it, I do see having to have another, let's say, recovery machine where we have to have enough airflow through the machine to ensure that if there is an internal leak in the machine that it stays below the LFL, those sorts of things. But yes, there are specialized tools that we're going to need to work with these A2Ls when they hit the market that are rated for use with A2Ls. And there's a lot of them out there already. Manufacturers are already putting them on the market. These are some good ones. All right, it looks like we've covered everything. If there's any additional questions, again, my email address is right there on the screen, and it's part of that thing that you downloaded. There's a question here. Will there be a de minimis undetectable minimum leakage allowed for A2Ls? That's going to depend on the authority having jurisdiction, the leak rates, and what the detectors can pick up, what the sensors are allowed to pick up. I want to say it was 0.3 ppm or 0.3 ppm. It's not going to change from what we require from A1 refrigerants. A lot of people don't realize that we require A1 refrigerants to be leak-proof or gas-tight systems and have this very low leak rate. We have the same requirement for these A2L refrigerants, as well as the A3s. But that'll again go down to everything that we covered today. Again, is based on a national accounting of what's going on. Things may be different in the local area that you live in. There may be where, let's, for example, we brought up M1, M2 charge allowed by the standards and system design, and then, but there may be some locales that say, listen, we only want M1 charges in our area, no M2. So again, it's going to come down to the local authority having jurisdiction on a lot of these things. I can tell you that the amount of testing, the amount of time, energy, and effort that has been put into developing this information and training to bring everybody in the industry up to the same level, that safe level of operation, has been monumental. And I'm happy that I was able to be a part of it. The high tide should lift all boats, so to speak. Do A2L leak or leave corrosive? Now, A2L refrigerants, if it's an A, it's a non-toxic refrigerant. 2L again refers to the flammability level. So there's nothing, again, if we had an R32 system and an R410A system and they were like, there's no difference in the, again, it's an approved ASHRAE approved refrigerant standard 34 with an A classification rating, non-toxic. And again, there are some good studies. Links have been posted with images and video to the studies that were done by the UL, by AHRI, by ACT. There's a ton of people in the HVAC industry that were in on this testing. And the information is, again, freely shared. It's on the internet. I implore you, if you're looking for more information, look up those AHRI studies. They were pretty good. The UL studies, I should say. With that, I'm going to close this out. Again, you have contact information if you want to reach out. You can contact either Heatcraft or myself. Again, my email address is on the screen. I want to thank everybody for tuning in today, being a very professional audience there. And again, I got to say, we're all going to move forward. We're all in this together. And it's my belief that if we're all well informed and ready for it, that it's not going to be a very large bump in the road. It's just going to be a very smooth transition. And I do want to say thank you.